All right, so I guess we can now start. Is it recording? Maybe I stop recording. Oh, it's not recording. I guess we could start from now because what I said before didn't need to go to YouTube. All right, so the topic, is there any questions before we start? Any concerns? Okay, so the topic for today is geometric optics. Of course, on FRW cosmology, so we continue our discussion on cosmology, but now we want to talk about photons and null geodesics in general. So what is geometric optics? The idea is that we want to work in the limit that we have photons with high frequency or short wavelengths compared to the curvature lengths of the background, and we want to just consider them as point particles that move on this background geometry, massless point particles that move on this background geometry, and we want to study their motion. And of course, the motivation is that the observation, the cosmological observations are made using this high frequency photons, and recently also gravitational waves and electromagnetic waves, that to a very good approximation, they just propagate on this curved background without being disturbed very much. Okay, so the first thing is that let me remind you that we wrote the metric, we introduced the conformal time to make it easier to think about the propagation of light or null geodesics. So we introduced the conformal time. So if you remember, the metric, FRW metric, had this form, times the spatial metric. Where this R contains the information about the spatial curvature. So depending on whether we are on a closed, flat, or open geometry, this R of chi would have different functional dependence on chi. Either it is sine of chi or chi itself, or sine hyperbolic of chi. Okay, and then we define the conformal time to be via the following relation. We said that a d tau is equal to dt or tau is equal to integral dt over a of t. Tau is a function of t. So this is the conformal time. And in terms of the conformal time, the metric looks like this. Now, one thing that might be slightly confusing is that I use the same variable tau for the conformal time that I used to use for the proper time of the observers. So here is this tau is not the proper time of the observers, is the conformal time. Sometimes it is called eta. All right, so now so here this is useful because if we consider, imagine that we are sitting at the at chi equal to 0 and consider null geodesics that arrive to us from the past, or in other words, if we look at our past light cone, then we can draw it in a tau chi diagram as 45-degree lines. But that is supposed to be a straight line. And so now, depending on what kind of FRW cosmology we have, often we will have a singularity at tau equal to 0. So for instance, we saw that there is a singularity, Big Bang singularity, when we have matter-dominated universe. And then often we care about our past light cone. So this is, and we put an index 0 to denote things that correspond to the current time. So we are sitting here and looking at the past. So what is the equation for this geodesics? Clearly it is chi equals tau naught minus tau. If I look at radii, null geodesics. So in particular, at tau equal tau naught, chi will be 0. So they arrive to us. All right. So now what do we want to consider? We want to consider the following experiment. We want to say there is another friend of us. Say Alice lives at some time tau, and Bob lives at tau naught. Alice sends photons signals to Bob with frequency omega A. And we want to see what will be omega B, what is the frequency of photons when they arrive to Bob. Of course, this is an imaginary situation, but the realistic experiment is that we have stars and supernovae and other astrophysical processes that send photons toward us, and they send photons with particular frequency related to whatever microphysics that governs that process. Say, for instance, it will be related to the temperature or the lines of various atoms that we have in that system. And now we want to see what would be the frequencies that we observe. What would be the relation between the two? Okay, so the procedure would be as usual, we look at the propagation of null geodesics along this in this radial direction. So we want to consider k mu, the 4 vector of geodesic that that moves in this radial direction, which means that it has these 2 components, the tau d lambda and the chi d lambda, where lambda is the affine parameter. And we want to solve the geodesic equation for this null ray. So if I look at, let's look at the chi component of this equation. Let me say actually something. Yeah, we can consider a simpler case first, just to illustrate the idea, and then consider the more general situation. So imagine this was we were on a flat spatial geometry. So this 3-dimensional metric was just the Euclidean metric. Therefore, this R squared of chi would be just chi squared, right? So then this is just the Euclidean metric written in radial coordinates. We could just go back to Cartesian coordinates, and this whole 4D metric would be just the Minkowski metric, right? In that case, we would have minus d tau squared plus dx squared plus dy squared plus dz squared if we go to Cartesian metric. So let's consider this. Flat case. K equal to 0. Okay, so now this k is a different k than that k, right? This k is the k that determines the spatial geometry. In this case, the metric is, as I said, it is a squared of tau times minus d tau squared plus dx squared plus dy squared plus dz squared. Now we could choose, for instance, this geodesic to be sent along x direction, for instance. Now, since we have isotropy, if I send it along x direction, it always propagates along x direction. Similarly here, if I send it in radial direction at some fixed, with some fixed choice of the angular variables, those angular variables remain the same just because of the isotropy. There's no point on these 2 spheres is preferred compared to any other point. So if I choose my photon to point in one particular direction along these 2 spheres, it remains in that same direction. Now, in particular here, if I send it along x, it remains in the x direction. Now, in this metric, we can see easily that there is no x dependence, right? And since there is no x dependence, there is tau dependence, but no x dependence. And we know that when the metric is independent of a coordinate, we will have a conserved quantity along the geodesic. So what does it mean? It means that kx with lower index is a conserved quantity, right? Because it's constant. Because the geodesic equation will look like d by d lambda of k mu equals 1/2 d mu of g alpha beta k alpha k beta. But if we choose mu to be x, then dx of g alpha beta is equal to 0. As you can see from here, there is no x dependence. And then we conclude from here that kx is constant. So now if kx is constant, then what do we learn? We learn that k mu is equal to, well, now we know what is the upper component of, we know that kx with x as an upper component is just that constant. Let's call that constant minus c. So I take it to be a negative value because this is an array along our past light cone. So it's actually moving from larger values of x towards 0. If I imagine that I am sitting at the origin. So that's why I take this to be negative. So kx with upper components would be minus c divided by a squared. And then since this is a null vector, the full k mu vector will be c over a squared minus c over a squared, 0, 0. Any question about this? All right, so we determined what happens to k mu. We solved for the time dependence of k mu. Now we can ask what is the frequency that observers measure, right? So omega is the frequency that an observer with 4 velocity u mu measures. Is how do we determine it? We go to the rest frame of that observer and look at the 0th component of the momentum of that null geodesic. So in the rest frame, in a local inertial frame that is instantaneously at rest with that observer, then that 0th component will give us the frequency, and that is equivalent to looking at the u mu times k mu. Now consider u mu for a co-moving observer. So remember we defined co-moving observer before. Those are the observers who are sitting at fixed spatial coordinates and just move in time. So in t coordinate that the 4 velocity was 1, 0, 0, 0. In tau you can translate it. We can determine what it looks, and we'll find that this u mu times minus u mu times k mu is equal to c over a, which means that omega times a or omega alice times a alice is equal to omega bob a bob. Or if we say Bob lives at the current time, so we put an index 0 for Bob, and then Alice is at some generic omega, then we have omega is equal to omega naught a naught over a. So in particular, in an expanding cosmology, as we go to the past, the scale factor is smaller, right? So this ratio a naught over a is going to be larger than 1, because as we go to the past, a becomes smaller than a naught if we are expanding. And I'm assuming a is, we are considering the tau, the time the photon was sent was to the past of us. We are looking at our past light cone. Maybe here is a good time to restore this time coordinate, tau, omega of tau. So this factor is larger than 1, which means that the frequency that we observe is less than the frequency of the photon when it was sent. This is called redshift. Of course, you are familiar with redshift. And one defines a quantity z via the following relation. It defines z to be this factor a naught over a. So it's a function of time. So z is called redshift. So in particular, at the current time, at tau equal tau naught, this ratio is equal to 1, and redshift is 0. So now there is 0 redshift, and then as we go to the past, this ratio grows, it becomes larger than 1, and therefore z grows. So in a sense, z acts like a time variable for us. It's a time variable that moves backward. So as we go towards past, z grows. As we move towards today, z becomes 0. So it's a backward time variable. Why is it a useful time variable? Because we do a spectroscopy. We measure frequencies of various atomic lines, for instance, or frequencies of things that we know what they were at the time of emission. So therefore, we directly determine this redshift factor. If we see that there is a supernova and there are hydrogen atom lines, but they are shifted to some amount, then we immediately know what is the redshift of that supernova, or what is the redshift of Alice. If we have an agreement with Alice that sends signals at I don't know, at some particular frequency, say at 1 eV, then if we measure the signals that Alice sent to us at this time, and we see that those frequencies are 0.1 eV, we know that 1 plus z is equal to 10. So this is something that we directly measure, and therefore it is very common in cosmology to talk about time in terms of redshift. So use z as a time value. So we don't say what is the time tau of Alice, we say what is the redshift of Alice, because that's the thing that we directly measure. Okay. Now let's, or maybe let me do one extra step still in this flat situation, flat cosmology. So let's consider this example of matter domination. So in matter domination, previously we solved tau as a function of t, the cosmic time. So we saw that tau is given by, so this is, I'm just copying it from the previous lecture. It's given by 2/3 t to the 1/3. We can also write it in terms of the scale factor. We can write tau as a function of the scale factor. So it becomes 2/h0 times a to the 1/2. Note that it has the right dimensionality, because h0 has the dimensionality of 1/time. A is dimensionless, and tau therefore has the dimension of time. Okay, now we know we have a definition of the redshift. Oh, another thing to mention is that here, since we are in flat cosmology, we can always rescale the coordinates so that a0 is equal to 1. So this a, you can think of it as a/a0, because a0 is 1. So we can write this expression as 2/h0 So if we want to write it in terms of the redshift, we can write it as 2 over h naught square root of 1 plus z. So this is an explicit illustration of why z can be thought of as a time variable. As tau as tau grows, z becomes smaller. As tau becomes smaller, z becomes bigger. So we can trade time with z, with Redshift. Okay, any questions so far?
In the last formula, you rescale A0 equals to 1, no?
Yes.
Okay.
Yes, because it's in because we are in the case of flat cosmology. In the case of flat cosmology, when k is equal to 0, you can always rescale these co-moving coordinates to set the scale factor equal to 1. In other cosmologies, it is common, if you look at various textbooks, it is common to, again, set a naught to 1, but that would be at the expense of having k, the parameter of curvature, to be not equal to 1 or minus 1, right? Because if you think about the way we write the metric in originally, it was dr squared over 1 minus k times r squared. So if I rescale r so that I make the scale factor at current time to be 1, then in order to, then I have to, my k would be different than 1. Will be if k is non-zero, then it will be changed. If k is 0, then there is no problem. So what happens is that in various books you might see relations for this r of chi that is not as simple as what I wrote. So what I would write for this r of chi would be sine chi when k is 1, chi, and sine hyperbolic chi, k is 0 and k minus 1. In textbooks or other notes, when they set a0 to 1, then these relations will be slightly more complicated. So it's up to you which notation, which convention you'd like to use. Okay, so now we can go to the general case. So all of this was in the case of k equal to 0 in the flat case. Now I can show you that the situation doesn't change much if we go to the general situation when we are on open or closed cosmology. So let us switch to general K. So here is the So here's the problem that we want to consider, but now for general K, the spatially curved cosmologies, not the flat. Well, it's still the same. It's very similar arguments. Argument can be applied. How if we can look at the chi component of the geodesic equation again. So d by d lambda of k chi. So what is it equal to? It is 1/2 d chi of g alpha beta k alpha k beta, right? Now, if we look at this factor, we see that this is equal to 0 unless alpha and beta are equal to theta or phi. Because only the theta and phi component of the metric depend on chi. Right? If you remember the form of the metric here. So it's only the theta and phi component that depend on phi component of the metric that depend on chi. This part of the metric, the tau and chi component of the metric, they don't have any chi dependence. But on the other hand, only tau and chi component of k mu are non-zero. So if we look at the second factor, this is equal to 0 unless alpha and beta are equal to tau or chi. So therefore, this whole thing is equal to 0. The right-hand side is equal to 0, which means that k chi is equal to constant. And then the rest of the argument follows as before. So again, the signals that were sent at earlier times, they will be redshifted by the same factor, A naught over A. Any questions so far? Okay, so now we can, for instance, ask the following question. Imagine now we think of Alice as being some source, like a supernova that has a given luminosity. And we want to ask what is the flux, energy flux that we measure at later time. So again, this is a useful question to ask because there are objects which we call them standard candles, for which we know or have an idea of what is their luminosity, what is the amount of energy per unit time that they emit. And by measuring their flux at later time, we understand we understand the cosmology, right? We understand how the distances are changing with redshift. Or basically, what is A of tau? What is the in what way the scale factor is evolving? And of course, that determines, or that that is related to the history of the universe. So that's eventually that's the goal, to understand the time evolution of the scale factor, and using that determine the energy content of our universe. So we want to ask so this is something that then allows us to define something called luminosity distance, something that people call luminosity distance. So let us again look at this. So what we want to consider is that there is a source here. And now we want to we want to imagine. So there is a source here, and we know what is its luminosity. So luminosity is energy per unit time. So we know its luminosity measured by a local observer at that time. Total energy per unit time that was being emitted at that time. And the question we want to ask is that what is the flux today? The energy flux today. So what is flux is energy per unit area per unit time. So how do we determine that? So the idea is that we can think about, again, photons. And of course, we want to work in this geometric optics approximation. So all photons that were emitted by this supernova or this explosion, they all travel towards us without being absorbed or without interacting with anything. They are just moving on this curved background. So all of those photons arrive to us sooner or later. And they are also, again, there is isotropy. So say the source is isotropic, so they will arrive to some sphere here in an isotropic way. So those photons are distributed uniformly over a sphere that is determined by the forward light cone of this supernova. So if I want to, maybe I can try to make it a bit 3D. Okay, so the first thing to ask is that what is imagine, let's consider one particular type of photons with frequency omega at the time they are emitted. So then we know that omega naught, so let's focus on one type of photons. By one type, I mean one particular frequency of photon. So then we know that omega naught is given by omega divided by 1 plus z. There's also a rate of emission of that particular kind of photons, right? An observer who lives near that supernova, that observer measures that these photons are being sent with a particular rate, number of photons per unit time. So that rate again is a frequency, and that rate will change between the two times. So the rate here and the rate at a later time are related exactly like a frequency. Rate is a frequency. So therefore, if I talk about the rate of the emission of photons at time 0, that will be the original rate divided by 1 plus z. So remember, rate is 1/2, just like frequency. So omega naught times this rate at time 0 is equal to omega times rate divided by 1 plus z to square. Now we can sum over all the species of photons, all frequencies of photons, and if we sum over all of them, omega times rate for all of them, that would be the luminosity, right? And we see that there is this overall factor, so it doesn't depend on the frequency. So what does it mean? It means that the total luminosity at time 0 is the original luminosity divided by 1 plus z squared. But this total luminosity is this total energy per unit time is distributed over this sphere, right? So now we want to understand what is the flux. So we divide this by the area of this sphere. So what is the area of this sphere? So area at tau naught is just 4 pi r squared when r is measured at chi of tau, right? So we understand what is this chi coordinate associated to the supernova, and then we just want to calculate the area of the sphere, and there is of course a factor of a naught squared, because in my notations a naught is not, my conventions a naught is not necessarily 1. So the area of the spheres are of course determined by this r coordinate times the scale factor at the particular time, and r we are talking about r of this this value of chi. So what is chi of tau? It is chi of tau is just since we are in conformal coordinates, chi of tau is simply tau naught minus tau. So therefore, the flux at time 0 is just L, the original luminosity, times 4 pi a naught squared r squared evaluated at tau naught minus tau times 1 plus z squared. So notice that this whole factor is just a function of z, right? Because tau itself is a function of z. As we saw before, we can trade time with redshift. So this whole thing is a function of z, and this is the object that is defined as the luminosity distance. So if we were just in Minkowski space-time, then the flux would be what? The flux would be L divided by 4 pi d squared, when d is the distance measured in this in Euclidean space-time between the source and the observer in Minkowski. So now the luminosity distance is defined so that we can write this as L divided by 4 pi dl, luminosity distance square. So the luminosity distance as a function of z is a naught 1 plus z squared. No. A naught 1 plus z times r of z. Or r of tau naught minus tau of z. So again, let me recap. L, so we have a standard canvas for which L is known. And if not, the flux is measurable. So when we know L and we know if not, we can determine, and we of course also measure the redshift. So we determine the luminosity distance as a function of the redshift. And that gives us a relation that allows us to determine the tau as a function of z, which depends on the particular history that we have. Or r as a function of z, that depends on the history. Any questions about this? Okay, if there is no question, then we can ask another kind of question. So of course, one point is that there is a lot of degeneracy in this problem, right? So we basically measure one function of z, but you could imagine, for instance, there are various unknowns in this system. Like you can have different matter contents, or we can have energy contents, or we can have different spatial curvature. So one often needs to find different probes of the geometry in order to break those degeneracies. The particular variables combine together to give us one observable, but they combine in different ways in different observables. So therefore, we want to look for different observables to break the degeneracy and determine various unknowns. So that's what we are trying to do. So what is another way of getting a handle on the geometry in this FRW setting? The other handle is to imagine that we have things that are called the standard rulers. So things that we know their size, and then we observe them at different. So imagine you have a ruler with a fixed physical size, and then you take that ruler and take it far away from yourself. So then we can look at the angular size of that ruler as we take it far away. You can also imagine that there is an atomic clock or a laser pointer on this ruler, so it's sending us photons. So as we take it away from ourselves, or as we take it to the past, we also measure the redshift of this photon, these photons. So we know the redshift, and then we measure also the angular size of this ruler. Then again, the variation of the angular size with the redshift is another measure of the curvature of a spacetime. Another combination of these variables that determine, that enter that relation between the angular size and the physical size of the ruler. And that is something that we use to define what is called angular diameter distance. Oh, and by the way, these rulers might sound a bit artificial to you, but actually we do have the standard rulers in cosmology. So there are things that we know their physical size at the particular time with relatively good accuracy. I guess the most important one is what is called the BAO scale, baryon acoustic oscillation, which is the distance. So this is something that perhaps we will see or talk about a little bit, or maybe not in the following lectures. Is a particular distance that the sound waves travel in the photon baryon plasma that we had in the early cosmology. So it's a microscopic distance that we can determine, and then we can see that particular distance when we look at the correlation functions of in the sky. When we look at, say, galaxies, we see that the distribution of galaxies have a particular correlation at that distance. So there is this distance that we can use as a standard rule. So it's not totally fictitious. So let us see what kind of question we want to ask. We want to consider our past light, and now I want to show some angular dependence. So we have our past light cone. And then on this, we want to consider two photons that are separated at some angle. So there is, say, there are these two photons. So we are here, and there are these two photons with angle emitted at two different angles, which is delta phi. So with a small relative angle. As I mentioned, because of isotropy, if I send them in these two photons at two different directions, their phi and theta coordinates remain the same. So in particular, I consider them to be on the equator at theta equal pi over 2, and with some phi with phi difference. So if we were on flat geometry, then the distance between these two photons would be just delta phi. The physical distance would be just delta phi times the time that we go past on Minkowski, or times the radial distance. But this radial distance on Minkowski is just the time, Minkowski time. So of course on our curved geometry, then delta L is some function of z as we go back in time. And the question is that what is delta L? This is the physical length. What is delta L divided by delta phi? And this is what is called the angular diameter distance. Now this is relatively easy to determine just by looking at the form of the metric. So as I mentioned, as I send these signals to the past, the phi coordinates remain the same because of isotropy. So all that I need to do is to look at my metric at some redshift z and ask what is the distance between 2 points on the sphere at theta equals pi over 2 and delta phi with some delta phi. So let us just copy the metric. So here's our metric. So what is this delta L? I just need to, not this time, I just need to look at this angular part of the metric. And the distance, the physical distance between these 2 points at redshift z is just going to be, oh, well, let me write delta L. So delta L at redshift z is just going to be a as a function of z times r of chi as a function of z times delta phi. So therefore, dA of z is equal to A of z, which now we can write it as, so remember that A was given by A over A naught was 1 over 1 plus z. So this A of z, I can write it as A naught divided by 1 plus z. So the consistency check is that as I go to larger z, A becomes smaller because I'm going to the past. So so this is consistent with that expectation. And then I have R of chi of z, which is just tau naught minus tau, which is itself a function of z. So now in particular, we can ask in a matter-dominated universe, when we determined, where we determine everything. So in particular, we know what is tau of z. Remember, tau of z was given by 2/h0 times the square root of 2/h0 times h0 times the square root of 1 plus z. So here, for instance, we can determine dA of z to be 2/h0 1/1 plus z minus 1/1 plus z to the 3/2. So here I asked this slightly different question, right? I fixed the angle and asked what is the physical distance, instead of fixing the physical distance and asking what is the angle. Of course, these two are closely related to each other. So this angular diameter distance has an interesting behavior in matter-dominated cosmology. So if I look at as a function of z, so what is the expectation at short times? At short times, we expect that the relation is just the relation should be just linear, right? So if if z is near 0, then as I move to the past, the distance would just linearly grow with z, or chi would linearly grow with z. And then at short distances, we are effectively we are close to Minkowski. We don't see the effect of curvature. So this distance would just grow linearly. But then at larger times, so this is what you can verify by looking at this form of this expression. So at a small z, there will be a linear relation, just expanding for z much less than 1. So this angular diameter distance grows for 1. And this is the natural expectation for in flat space-time, right? The distance will just grow. As you go to larger times, the distance just linearly grows. So remember this, if we were in Minkowski, as we go past in time, this radius grows in the same way as the Minkowski time grows. So we would just have a linear relation. But then at larger times, it changes because of the curvature, and then it will go back to 0. So it will have a maximum. What it means is that if you now consider a standard ruler and you take it back in time, then as expected, if you have a standard ruler and take it far away, the angular size shrinks. So it becomes smaller and smaller with time. So this is the natural expectation in flat space-time. But the fact that this angular diameter distance turns around and becomes smaller, it means that as you take it back in time, then it starts again growing. So your natural ruler will, your standard ruler look like shrinking as you take it past and then grows again. There will be a time and a minimum angular size of the ruler. Okay, any questions so far? Okay, if not, then maybe I mentioned something about Blackbody spectrum. On general curved spacetime. So again, the reason this is perhaps a more general situation compared to what we already saw when we talked about the luminosity distance. So we saw that if you have some source which sends photons with some frequency and with some particular luminosity or some rate, we saw how it changed, how the flux that we observe changes as a function of time on a FRW cosmology. Now there's a more general statement about the motion of if you have an ensemble distribution of photons in the geometric optics approximation, and they move on a general curved spacetime. Then there is a general statement about how the behavior of this motion, which follows from the Liouville theorem. The fact that the volume of the phase space of these photons will be conserved under the motion. That has an interesting implication, which is the following: if you have a source, which, for instance, if you have a source which has some blackbody spectrum with a given temperature, so let us consider the source. It could be sun or some faraway object. Then the photons that are emitted, so this has a blackbody spectrum as measured by a local observer at the location of this. Now imagine these photons propagate on a curved spacetime and arrive to us who live far away. So this spacetime might be expanding. There might be some gravitational potential there that they are climbing out of, so they might redshift or blue shift as they arrive to us. Now the statement is that if we consider a very narrow cone, so let's imagine these photons that travel, they have some very complicated history, a trajectory until they arrive to us. So I'm not sure if I can draw this very well. So we want to imagine want to imagine that they go through a very complicated history until they arrive to us. But they are always in the geometric optics approximation, so they have frequency which is larger than the curvature. And then the statement is that if we consider a very narrow cone, so if we consider some extremely narrow cone, so imagine we look through a very narrow cone through which we only see that source. So for sun, it is easy to consider because sun has a big angular size in the sky. But perhaps for a faraway star, it's much harder. This cone has to be really narrow. But imagine we can come up with a very narrow cone that only sees that object inside it. So it's fully covered by that object when we look through the cone. Then the statement is that if we look at the spectrum of photons that we receive from that source, it will still have a blackbody spectrum, but perhaps with a different temperature. The only thing that can happen to this distribution of photons is that they will change their temperature, but still they follow a blackbody. They have a blackbody distribution. So what is the blackbody distribution? It's just a statement that, so let us consider some box with size L. Or it could be, of course, this box is just a tool to derive this result. It doesn't. The details of the shape of this box is irrelevant, but it's a useful tool. So let us consider this box, and then we know that we have in the box. If we consider photons or electromagnetic waves in a box, they'll have discrete levels. Say this is a periodic box. Then you have discrete levels because momenta of photons will be quantized. So we will have k, for instance, kx given by 2 pi nx over L. And similarly for ky and k, or actually, let's say ki is 2 pi ni over. And then we know that in thermodynamics, if I have this box at temperature T, then any energy level has an occupation number or expected occupation number nk, which is 1 over, so this is just the Bose-Einstein distribution for photons which have 0 chemical potential, and this is given by e to the minus omega over t, sorry, plus omega over t minus 1, where omega is just the size of the k vector. So I'm in natural units, and I set Boltzmann constant to 1. Now, if, for instance, we want to look at the total expectation of the total number of photons, we should just sum over all of the energy levels. And we should also remember that photons have 2 polarizations. So therefore, for any k, we have 2 degeneracy of 2. In general, we can call this G. This degeneracy, internal degeneracy or polarization. So we get a relation that the expectation of the total number is a sum over all energy levels, which is discrete in the box, but we can approximate it by an integral when we normalize the d3k, the measure of integration, by 2 pi over L cube. Times 1 over e to the k over t, where this k is not just the magnitude of our vector k, minus 1. And if we want to ask about the, also let's also do some extra thing. We can ask about the number density of photons by dividing this by L cube, the volume of the box, and that is given by G times d3k divided by 2 pi cube 1 over e to the k over t minus 1. And remember that G is equal to 2 for photons. Now, similarly, if we want to measure the energy density, then that would be given by, so the energy of each photon is h bar times omega. In natural units, h bar is 1, omega is k, so that would be the same integral, except there is an extra factor of k or omega. Okay, so this is called the Blackbody spectrum. This distribution of photons in the phase space as a function of momentum. So in particular, I can ask, what is the number of photons that what is the number of photons that arrive to some particular element of area. So I consider some delta A, some infinitesimal element of area, and I ask, what is the total number of photons that arrive in time, some short time interval delta t to an element of area delta A with some frequency omega, and in some solid angle delta omega, and in some range of frequency. So let me say in the range of frequency omega to omega plus delta omega. Right, so I sit here and count the number of photons that arrive to me. In some particular, some small, some short period of time, and in some solid angle. So then that can be determined by looking at this expression, right? Because we have the number density of photons. We know how they are distributed in various directions. So what we can do is that we can just rewrite this expression as this n. We can rewrite it as g integral dk times d omega times k squared divided by 2 pi cube e to the k over t minus 1. Then the answer to that question, or maybe another question would be, what is the amount of energy that I receive here? So that has a name, it's called the specific intensity. The amount of energy that I receive in that direction, so that it's called I of omega, and what is it? It's energy per unit area, per unit time, per unit frequency, per unit solid angle. So since photons travel at the speed of light, this delta t corresponds to delta x, right? We are talking about photons that move perpendicular to this surface. So in some time delta t, we would be looking at some distance delta x equal to delta t. So all that we need to know, or we need to do, is to count all of the photons in this box with size delta t and normal area delta a, one side delta t and normal area delta a. We count all of the photons that move in this particular direction and in a range of frequencies delta omega. And in the so that is basically the measure of this integral. And since we have the density here, so that would be that counting all of those would be multiplying. So that number would be just G. So this would be number per unit frequency, hertz per unit stadium, would be G times k squared divided by 2 pi cube e to the k over t minus 1. Since this is the density, then we multiply by delta A and multiply by delta t, since C is 1 in our unit. So delta A times delta t would be just the volume of this box. Now, if we also want to divide, if we want to now measure per unit area, per unit time, then we divide by this factor. And since we want energy, we multiply it by another factor of k or omega, because every photon in this range has energy k. So what we get for this object, which is called the specific intensity, is G times k cube times 2 pi cube e to the, okay, so I called it a function of omega, so let me just switch from k to omega. Omega is the same as k. Okay, so the statement is that, so maybe we can continue this discussion later. The statement is that if I look through this narrow cone and I see some object that is sending blackbody radiation, then through this narrow cone I will see. So this is exactly the kind of question that we would ask when we look at through this narrow cone. We observe a flux of photons that arrive to us in a particular solid angle and in particular range of frequencies. Then the statement is that what we observe, this specific intensity that we observe the specific intensity that we observe will follow the same equation, the same relation with frequency, except that the temperature is modified. Now, this is something that in the case of FRW cosmology is very easy to verify, but the statement holds much more generally as in this geometric optics approximation, and it's just a consequence of the Liouville theorem, the conservation of the volume of the phases, which we can continue discussing in the future lectures. Okay, so that's it for today. Are there questions? Okay, if not, then see you on Friday at the usual time, at 2. Thank you.
Thank you.
Thank you.
Bye.